Okay, so back to alias. Aliasing causes a new signal near the original to be created. The signal has a frequency of fs minus fm. So when converted back to analog, the output will be the alias rather than the original signal. Sometimes it's a problem, sometimes we want it. So here in this case, we have FM over at 2 kilohertz, and then our sampling frequency is 2.5, which is too small, considering that we need the sampling frequency to be at least 4 kilohertz, right? The requirement of the Nyquist tells us that Fs is greater than 2 FM, assuming the signal starts from 0 hertz. So this would tell us that if FM is 2 kilohertz, this would be 4 kilohertz, right? But in this case, the sampling frequency given is 2.5, which is too small. So what happens is the aliasing will happen, and this will happen in two ways: FM plus Fs as well as FM minus Fs. So this will give us a value of 4.5, and this will give us a value of 0.5 kilohertz. Now the 0.5 kilohertz is going to be situated in the first Nyquist zone. So this is what's going to be translated as the signal when it's converted back to analog. Okay, so we know that aliasing happens when the sampling rate is smaller than the Nyquist sampling. So assume we have an FM of 2 kilohertz. The Fn should be 4 kilohertz, but in this case, the sampling rate is given as 2.5 kilohertz, which is less than the Nyquist sampling needed. Okay, so FM is represented by this green thing or turquoise. Okay, this is our FM, and we are assuming this is going to be our 2 kilohertz. So if I am sampling at Nyquist sampling Fn of 4 kilohertz, it means that I need to go twice as fast as this frequency. Okay, twice as fast. So if one complete cycle is here, I would need to sample here, 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 like that. So it's sampling twice as fast as the frequency FM. That is the best, following the minimum requirement of Nyquist. But in this case, what you're sampling is Fs is equal to 2.5. It is faster than FM, but not as fast as we want it to be. So again, if I start here as my sampling point, if I complete one cycle, which is 2 kilohertz, it would stop here. But my Fs is 2.5, which means that it's slightly faster, and that is why it sampled before the complete cycle finished. Complete cycle is 2 kilohertz. If I sample earlier, it means that I'm sampling at a frequency higher than 2 kilohertz. The best sampling would have to happen here, but it's not the case here. What they're doing is 2.5 kilohertz when it should have been 4 kilohertz. Very fast. Okay, again, let me try to explain this again. I know this is not very intuitive for most people. Okay, so if we are sampling at 2 kilohertz, let's try to say that we are sampling equal to our Fs is FM, 2 kilohertz. So if I start here, 2 kilohertz would mean that I am sampling here. That is, if it is following FM. Maybe I need to indicate it like this. Okay, 2 kilohertz is pink. And then Fn, or 4 kilohertz, where should it be? Fn, or 2 kilohertz, I would start here. The next sampling would be there. If I am sampling higher than FM, but still lower than Fn, I would sample at a frequency faster than 2 kilohertz, which means that it's going to happen before the pink X, but it's going to happen later than the green X. So this is where it is sampling. Starting from here, the sampling is 2.5. Faster. Okay? Faster happens before the complete cycle. The best is half of the complete cycle. But this is not the case. So when we are not sampling at the best sampling rate or the minimum sampling rate, we are going to cause aliasing. So if it is sampling at 2.5 kilohertz, this is where it would sample, and then we would reconstruct based on the sampling, this poor sampling rate, and reconstructing this would give us over here, 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 here. It's basically following, it's following the levels that we sampled. I can do it like this, but in the end the capacitor would smooth it out. Of course, it's going to be looking squarish, but in the end we would get a smoothed out waveform because that's we have the capacitor. Okay, now let's zoom out a bit. Okay, so how do we overcome aliasing? So a low pass filter called anti-aliasing filter can be used. It is placed between the modulating signal source and the A to D converter. So this is our modulator, and then we have our anti-aliasing filter, and then we have our A to D converter. Okay, so, and this ensures that no signal with frequency greater than half of the sampling frequency is passed. Half of the sampling frequency. The filter must have good selectivity, steep roll-off or steep skirt, which means that it's very steep. The filter cutoff is set just slightly above the highest frequency of the signal. So here, this is just slightly above FM. This is FM. It is just slightly above and of the highest frequency of FM. Okay. And then we talked about oversampling. The greater the sampling rate, the finer the granularity of the digital version of the signal. Oversampling is always going to give us the best output, but it will cost us money. Higher cost, higher power consumption, increased memory size, increased need for faster processing. However, the advantages is that it preserves the signal content, makes anti-aliasing filter less complex if we oversample. The closer the upper frequency content is to the sampling rate, the greater the need for a very selective filter. So if FM is very close to FS, then you would have to have a very selective filter because you just want FM and not FS. So the greater the sampling rate, the smaller, simpler, and less expensive will be the filter. Because it produces many more samples in a given time, it has the effect of decreasing the quantization noise floor by spreading it over a wider frequency range. Remember, we talked about having more levels means that we will reduce the quantization error. And this improvement in SNR is called the processing gain. When we are reducing the noise floor, we are improving the signal to noise ratio, because remember, noise equation is given by this. Q is dependent on how small this is. So the smaller the Q, the smaller the noise. If Q decreases, then noise also decreases. So when we have a smaller noise, this actually improves SNR, and the improvement in SNR is called processing gain. So how do we calculate processing gain, and how much does it contribute to the improvement of the SNR? So the SNR is the ratio of the signal power to the noise power, expressed in decibels. So you have learned this. This is signal power over noise power. Log of this times 10 will give you SNR in dB. The process gain is computed with this expression. This is our sampling rate divided by 2 divided by the bandwidth. We convert this into decibels. This will give us the process gain. So it is dependent on sampling rate and also bandwidth. Therefore, the SNR total is SNR plus the process gain. So we have an example here. Assume an SNR of 68 dB, bandwidth of 20, and sampling rate of 100. So SNR is simply 68. Process gain, we would just plug in 100 as our Fs and 20 as our bandwidth. Convert this to dB, we will get this as 4 dB. So the SNR total is 68 plus 4 equals to 72 dB. So we started with 68 dB. After digitization, and because we oversampled, we actually improved our signal to noise ratio to become 72 dB. The improvement is by 4 dB. Next is undersampling. Undersampling is simply sampling at a rate less than the Nyquist rate. We have seen this happen before. What happens is that instead of getting the green guy back, we got this purple guy, which is way off. But sometimes we want it. And this is what we're going to discuss in undersampling. So Nyquist rate tells us that it needs to be 2 times the highest frequency in the signal to be digitized, or twice the bandwidth. This typically assumes that the spectrum of the signal to be digitized ranges from DC of 0 Hz to some upper frequency FM. But the Nyquist theorem also tells us that the signal to be transmitted can be retained all of its information if it is sampled twice the bandwidth of the signal. The disadvantages of undersampling is aliasing. It recovers a signal that is much lower than the original signal. Most of the time it's wrong. But the advantage for this is that we can use a slower ASC or a filter. Aliasing is used for mixing or modulation that is often done in radio receivers. We have seen this being applied in superheterodyne. So let's talk about the Nyquist zones with respect to undersampling. So the Nyquist frequency is shown and the spectrum is divided into segments called the Nyquist zone. Okay, a Nyquist zone is 1/2 of the Nyquist frequency. So Fs over 2 is the interval for each zones. So the first Nyquist zone will be from 0 to Fs over 2. The sampling process is amplitude modulation with a rectangular wave producing a spectrum that is a collection of signals representing the sampling frequency. So what's this telling us is that we talked about this just now. We had an analog signal, we convert it to digital, and it produces the signal at these frequencies, Fs, 2Fs, 3fs after we multiplied it with the